All right, good afternoon. Let's start the lecture. And what I'm going to do is I'm going to do a very quick review. This year somehow I'm running a little bit late, so instead of me writing here, I'll use some part of the review. I'll just show you the PDF file here. This is basically not really new, and actually, as Jonathan just noticed, that this is engineering applied science number 3. Sorry, engineering analysis 3, right? So the main topic that we're going to cover is basically linear quadratic optimal control. Okay, so it's an optimal control concept here. Okay, now to sort of lead into that topic, and I wanted to touch upon the topics here that we learned in the previous courses, which is basically your second year 248. So there's a category called optimization problem called unconstrained problem. Right? You know, unconstrained basically means this is an example giving you a function of 2 variables. I mean, in your first year you learn function of 1 variable, right? You know, have a y equal to f of x, and if you take a derivative, you let it equal to 0, then you find a critical point. And then you can do a second derivative test, and you find whether that's a minimum or maximum point, right? Yeah. And this is basically unconstrained problem here. And if you extend that to function of 2 variables, okay, function 2 variable, it's the same idea. So function 2 variable, if you plot it in 3D, it basically gives you a surface. Okay. Yeah. And I'm not sure how many of you still remember when I teach 248, there's one thing, and I tell the class, there's one thing you just have to remember, right, about the multivariable calculus. When you have a function of 2 variables, okay, and you take the gradient of that function, basically del f, what's the physical meaning of the gradient vector?
Direction of maximum increase.
The direction pointing to the greatest increase for the function f, right? Yeah. So that's basically what gradient means. So as you can imagine, if you have a function and somehow you are at the minimum or maximum location of that function, so guess what? The gradient of the function must be 0, right? So that's essentially the idea for the so-called first derivative test in comparison with the function of 1 variables there, right? And you set the gradient to be 0, and you find a solution. The solution is the so-called critical point for that function, basically. Okay? Yeah. Now, what if I have a function more than 2 variables? Then you can't graph that anymore. Then you can imagine you have a function of n, it's like n dimension, basically, right? You do the same thing. You take the gradient of that function and set it equal to 0, find the solution of that, that's your critical point, basically, right? That's called the first derivative test. But is this point, the critical point, a minimum point or a maximum point or something else, right? So how do we do that? Then we need a second derivative test, basically. Okay, so this theory essentially here is for function 2 variables. If you take a second derivative test, and you need to follow these rules that are here to find out whether it's minimum, maximum, or saddle point, or you can't decide, then you have to do a high order derivative test. Okay, yeah, that's what we learned previously. You know, basically in the previous lectures, right? You know, essentially, I'll write a few things that are here. Let's say if I want to minimize or maximize, for example, a function of n number of variables, okay? And we typically write it as vector format. So let's say j of x bar here, right? So that's, I use a j at here because later I use the g for the cost function, but you can consider this is basically a function here, right? It's a function. Okay, yeah. Okay, so first derivative test is the gradient, right, that equal to 0. Okay, yeah, gradient that equal to 0 here. And gradient that equal to 0, it basically means you're taking partial j over partial x vector at it here. Okay, then you're taking this whole thing equal to 0, and that is partial j over partial x1 to partial j over partial x n, okay, equal to 0. Okay, that's basically what it means. Okay. That's your first derivative test. Okay, yeah. Now, second derivative. Before I write down the second derivative test for the general case, and I need to write down the Taylor series, okay, for this function, okay, at x equal to x naught, okay, at a certain location, right? Yeah. So don't be scared by this multi functions here. You know, if you reduce that to single variable, two variable, right? It's the same idea, basically. Okay. So if I take a derivative, I take a Taylor series of this function, okay, around x equal to x naught, then the Taylor series can be written as this. So Taylor series is you have a multiple terms, right? So first order and then the second order here. And then plus all the higher orders, right? Okay. If you take a Taylor series, this is a general format for function of, you know, n number of vectors, or more than basically 2 or 3, right? Yeah. So if I look at this Taylor series expansion, you apparently see this is the first order term. That's your gradient vector at here, okay? And this is a second order term at here. A second order derivative test is basically looking at this second order term at here, right? Yeah. In particular, within this Taylor series of second order, there is another one, so partial j over partial x squared. And sometimes you write it as basically this is second order partial derivative, basically. Okay, second order partial derivative. Okay. And the second order partial derivative, if you expand it, okay, if you expand it out, see, this is the first order partial derivative, right? First order partial derivative. And you take basically, here's the first order partial derivative, and you take another partial derivative with respect to x, you get the second order partial derivative. And this one gives you a matrix called Hertzing matrix, essentially. Okay. And this so this Hertzing matrix, if you write it down every term, you get this is partial j second order with partial x1. All the diagonal term is second order partial derivative with respect to x1, x2, and xn. And off a diagonal, it turned out to be a symmetric at here. So this is partial j over partial x1, x2, and up to partial j over partial x1, xn, and here partial j x2, x1. I should write a partial here. Right? Partial x2, partial xn, partial x1, then partial x2, partial xn, here's partial j squared xn x1 xn x2. Okay, so this is called the Hertzian matrix. Okay, Hertzian matrix. Is that good? Yeah. Yes.
Just on the bottom there, is that also dxn and dx?
Oh yeah, that's right. Yeah. Good. Okay. So why I'm writing this down here is, let's go back to this Taylor series at here, right? Look at this Taylor series expansion, and then we know this is a Hertzian matrix at here. Okay. Yeah. So what does second derivative test means? So let's say you do a first derivative test, and you find that x equal to x naught is the critical point. Okay, for example. Okay. So you do the first derivative, you find the critical points at x equal to x naught. And then you look at the Taylor series expansion. So if this is a critical point, basically means the first term must be what? 0, right? Must be 0, because you're at the critical point, right? Either basically crossing the axis. Okay. Sorry, not the first term. At the critical point, which one is 0? This term is 0, right? This term is 0. Okay? Yeah. And this Taylor series expansion, you can move this term to the left side. Okay? Move this term to the left side. So basically, what you're doing is you're comparing a point near x naught with the value at which point? At the point x naught, right? So it's like it's hard to draw it here. You're at this x naught location, and you move away a little bit, and then you're at this x location, right? Yeah. So you're comparing the value with between these two at here. So that's what you get, this minus this, right? Yeah. So that minus that, you will get a delta G, right? Okay. So you get the difference between here and the critical point. Okay. And what is the difference? The difference, if I omit the high order, you only have this second order term here, isn't it, right? You only have the second order. Okay. So now imagine, if this point, critical point, is at a local minimum, okay, then if you move away a little bit, then any values around it minus this value should be greater or equal, or should be greater or less than 0. Should be greater than 0, right? So because this is minimum, then any values away from it is always bigger than that value. So you'll get basically this guy will be greater than 0. But that depends on what? Depends on this term. Depends on this term is greater than 0. That makes sense? Right? So basically the sign of this term, whether it's a greater than 0 or less than 0, determined whether this x naught is a minimum location or a maximum location, right? So the whole second term, the sign at here, determines the minimum or maximum value, right, for the g at here. Okay. So, and this actually becomes quite clear now. If you look at this term here, right? If you look at this term, so let me write down here. So 1/2 x minus x naught, and then partial square j partial x square x minus x naught. Okay, this is transposed here, and this one you take it at x naught. Okay, for this term. Okay. So for this term here, this is basically, first of all, it's in a quadratic form. Okay, this is in the quadratic format. So quadratic format basically means it's in the format like 1/2 mv square. That's quadratic. So second order, you have a x plus y squared. Those are basically called quadratic formats. Okay, yeah. But this is in the matrix here. So how do I determine the positive or negative information based on this thing, right? So how you do is you will have to in terms basically you look at the middle one here, this one here, the person matrix. So this is a matrix here, right? This is a matrix. Okay. The positive definite or negative definite, if you remember in the linear algebra, when you're giving a n by n, let's say, matrix, right? There's a concept called positive definite and negative definite. Do you remember that? Right? So essentially, if this G matrix, okay, is positive definite, okay, if this is positive definite, okay, so let's let A equal to this one here, okay, then A will be greater than 0. Okay, so this value will be greater than 0. If this is negative definite, then A value will be less than 0. Okay. So I'll give you one simple example. Let's say if I have a matrix G equal to A, B, C, D. That's a second order. That's a matrix of 2 by 2, right? That's a matrix 2 by 2. So what does the positive definite or negative definite matrix means? So then you can take a look at basically the determinant of all the sub matrices. So let's say if you see that A is greater than 0, and then this AD minus BC is greater than 0, okay, then that basically means this is a positive, okay, definite, okay, matrix. Okay, yeah. And if this is a scalar, G just equal to A, right? Then when A is greater than 0, you got a positive number, right? Yeah. So that's the idea of positive definite at here, or negative definite. Okay. So you can imagine if you have a positive value, right? If you got a positive value at here, so that means this minus this yield a positive value, then the x0 must be what type of position? If this is whole thing is positive, then this minus this is positive, meaning x0 must be a minimum location, right? Minimum location. Okay, so this is essentially the so-called unconstrained problem. Okay, so you're giving a function, and you want to find the minimum or maximum location, right? Depends on the function at here. You do two tests. One is the first derivative test, and the other is the second derivative test. Okay, yeah. And you can reduce this easily to a function of one variable or two variable, okay, using this general here. A second one here, okay, is more of our interest now. Okay, so basically this is so-called constraint problem here. Okay, constraint problem. So I'll use a very simple example to explain the constraint problem here. Okay, and this is also the concept we actually learned in 248. The formulation of the problem, let's see, let's give you example here, okay? A general example here. So we wanted to, let's say, maximize or minimize a function, giving a function of 2 variables, for example. Okay, so here's a function 2 variables here, and now we have a constraint here. So we'll see subject to g of xy, equal to c. Okay, g of xy equal to c. So that's the difference here, right? So you have a function 2 variable, but then now you have a constraint here. Now sometimes you just say subject to say st, subject to this constraint here, and a lot of simple examples here. Basically, you can fall into this category. Let's say, for example, right? Let's say if you are let's see. Anyway, I don't think we need an example here, but yeah, okay, I'll write down an example here. Okay. So let's say here is my function f of x, y here, okay, and then this is subject to, let's see, this is subject to g of xy equal to xy equal to 3. Okay. Good? Yeah. Right? That's one simple example right here. You can understand this. You can try to understand this one as this. Basically, if you look at x squared plus y squared, you can try to understand this is essentially what the distance square, right, from any point to the origin. Okay, so this is basically distance squared to the origin, right? And now the xy is not an arbitrary xy here, right? The xy has to be on the xy equal to 3 curve, and xy equal to 3 refer to essentially a parabola, that type of curve like this. Okay? So basically what we're looking for is what is the minimum distance, right, from any point, okay, along this parabola here to the origin. That makes sense? Right? Yeah, that's the formulation of the problem here. Okay? Yeah. And of course, I can also understand this one purely mathematically. So like this, z equal to fxy equal to xy squared. Okay? This is basically, if I plot it, we get a so-called paraboloid. Okay? So this is a surface. Okay? This is surface z equal to x squared plus y squared. Okay? Yeah. So if I only look at this single function here, this single function, and if I forget about the second one here, just the first one here, right? If your ask is, can you find the minimum value for this function? That's pretty easy, right? Where is it? It's right here, isn't it? Right? It's 0, 0. Okay? Yeah. But now the problem is what you have is a constraint. So the xy is not an arbitrary location in the xy plane. It is constrained to, if this is xy here, so it is constrained to a curve, okay, over here, right? Yeah, over here. Is that good? Yeah. So now you can imagine, basically the same question becomes, if you're going to walk around, okay, this constraint, right? As you're moving around this constraint and here, imagine if you're at this location, and for this xy location and here, if you're plugging into this z equal to x squared plus y squared, then you will be over here, right? Okay. And as this dot moving along this xy equal to 3, and this dot here will move along the surface x equal x squared plus y squared. That makes sense? So you can sort of plot out. So as you're moving along here, it will move along the curve. So there will be a curve traced out as this point is moving along this xy equal to 3. Was that right? Yeah. So now you can see if I'm asking you what's the minimum value of this function subject to this constraint, you can literally not a precise value. You can say, okay, so it got to be somewhere here, right? Got somewhere here. It's not a 0 anymore, right? Yeah. So there will be certain values, but that's the idea, right? That's the idea here. And so for this type of problem, then how do we formulate and how do we solve this, the so-called constraint optimization problem, then, right? Yeah. So here's the rough idea of how you can solve it here. Okay. We actually learned this before. Okay. First of all, okay, we use the idea of the directional derivative. Okay, directional derivative. So let's say here's a constraint at here. Okay, and it's moving. So you're moving the point in the direction of u hat. Okay, so you're moving in the direction of u hat at here. Okay, yeah. So as you're moving in a direction u hat, you can imagine that this person, okay, on this surface, will also be moving up and down, right? And you also move down here. Okay. So number one, okay, there are a few facts here. So fact number one, okay, fact number one. Here is your constraint. Let's see. Okay, here is your here is the function you're trying to minimize at here. Okay. Number one fact is, if you take the gradient of the constraint g of x, y, okay, you take the gradient g of x, y, the gradient is always perpendicular to the tangent direction u hat. Okay. So basically, if you take the gradient, the del g, okay, will be perpendicular to this u hat at here. Is that good? Yeah. So that's the first fact at here. Okay, the first fact. Okay. Now, second fact. Okay, second fact. Before we write it down, the second fact here, and I need to write down the directional derivative, basically formula. Okay. Directional derivative. So what is directional derivative? First of all, what is the derivative, maybe, right? If you have a function single variable, then you take the derivative, you get the derivative, right? And derivative is the slope, and the derivative tells you basically how steep at that point is. Okay. So for this function right here, if you think about it, right, this black person, this person will trace out a curve on this surface at here. So for that particular curve, at any point, right, at any point, there will be a what? There will be a concept of a derivative, right? There will be a concept derivative. So at that point, maybe it's going down, or maybe it's going up. For this question, if you move to this direction, it'll go down, right? It'll go down. So that directional derivative basically is a concept of how much of this function f, so how much is this function f will change as you're moving along the direction of u hat. So if you move along the direction u hat by a small displacement ds, how much change this function f will be. Right. This is basically a derivative concept. If you take a derivative df over dx, what's the meaning? The rate of a change for the f with respect to what? To the change in the x, right? Here basically means the rate of a change for the function f when you're moving in the direction u hat by how much? By a ds of displacement. Right? That's directional derivative concept. And directional derivative has a formula, basically is the gradient times the u hat, okay, times u hat. So here's the direction moving, here's the gradient. If you dot these two together, they're vectors. Okay, if you dot the two vectors, then you get the directional derivative. Okay, directional derivative. Okay. Now, guess what? If this person starts moving along this curve right here now, at which point that the directional derivative will be 0? At the minimum, right? So if you got a derivative equal to 0, that basically means you're at this trough or the peak points, right? So if directional derivative, same thing. If you got a directional derivative equal to 0, meaning you're at this either maximum location or a minimum location, right? Yeah. So that basically saying what we do is, right, at critical point, the del f dot u hat equal to 0. Okay. So this brings me the second fact. Okay, the second fact. When you have two vectors, dot product is 0. That means the two vectors must be what? Perpendicular, right? Must be perpendicular. Okay. So if I go back to this drawing at it here, and I'll use a green color. When we draw del f, okay, del f is a vector size of 2 because this is a function of two variables here. Right, so this is basically equal to partial f over partial x, partial f over partial y. Right? Okay. So at this location, del g is always perpendicular to u hat. Okay, so u hat is a tangent vector to g, and del f, okay, will be perpendicular to the u hat too. Okay, so both del f and del g, the way I draw, okay, it's in the xy plane. Okay, in the xy plane. Okay, so now you can see fact 1 and fact 2. So based on these two facts, so you have in the same plane, right? So if I draw it here, so in the same plane, here is u hat, here is del g, and this is del f. But I draw the del f this direction. Maybe the del f is actually this direction. Who knows, right? Yeah. So you got both del g and del f are perpendicular to the u hat. So basically means what? The del f and the del g must be, the two vectors must be what? Parallel, right? So they must be parallel. Okay. And they are parallel then when you, if you want to use a mathematical expression to express two parallel vectors, that means that the two vectors must be only different by how much? A scale, right? Only different by scale. So I'm going to use the lambda here, okay, and we're going to use a negative just for the ease of writing it here. So we're going to use a negative lambda here to relate the two vectors. And this lambda here is the so-called Lagrange multiplier. The so-called Lagrange multiplier here. So it's basically, you see, the lambda connects what? Connects the original function f and the constraint, right? The g at here, right? That's the constraint. Okay. So now I have another equation, right? So basically I have g of xy equal to c, which is the constraint at here. So these two equations together will give you, actually in this particular case, will give you 3 equations. Okay, 3 equations. So you'll be able to solve for the critical point based on the 3 equations. Essentially you'll be able to solve for x, y, and lambda, 3 equations, and 3 variables at here, right? So yeah, f is in this, but you can have any other different type of f, basically, right? Yeah. Does that make sense? Right? So to further a little bit here, just to maybe, if I wanted to write this out in specific here, right? So del f is partial f over partial x, and partial f over partial y. Okay, so this is basically this vector here, and that equal to negative lambda partial g over partial x and partial g over partial y, and plus the last equation. Okay, that's what I mean by the three equations in it here, right? So you got partial f partial x plus lambda partial g over partial y equal to 0. Sorry, x here. Okay. Alright, that's the first two equation, and the last one, you got the constraint at here. Okay. Yeah. Three equations. You can solve for the three variables, and you end up with basically the critical points, the critical solution, right, for the x and y, and you'll get also the solution for lambda from here. That makes sense? That's basically the essential idea for constrained type of optimization problem. Yes.
What was G defined as in the first place?
Yeah.
On the original curve, I thought it was just perpendicular to u hat.
Yes. No, not G. G not perpendicular to u hat. G is just any arbitrary curve, right, in the xy plane in this case. For example, g xy equal to xy, right, equal to 3.
Okay.
Yeah. So if you draw it out, that's basically a parabola, right? Yeah. So this is basically, this is a curve, right? In 2D, it's a curve, and its constraint basically means your xy value cannot be anywhere except where on this curve. Okay? Yeah. But del g is perpendicular, so this is a g of xy curve. The gradients of this function will be perpendicular to its tangent vector u hat. Okay. Yeah. It's a very simple idea, basically, if I give you a curve which is, let's say, a circle, right? Yeah. Let's say this is x squared plus y squared. This is our g of xy. Okay? Yeah. And if you take the gradients of this function in here, it's the del g, it's perpendicular and perpendicular to the tangent vector, right? Okay? Yeah. So this is not the final form. We actually wanted to use that here. Now we have three equations here. Now next, I want to introduce basically or define a new function here. Okay, so introduce the so-called Lagrangian. So we're going to introduce a new function called the Lagrangian, and this function in this case here is defined as this: L function Ly lambda equal to f of xy here plus lambda g of xy minus c. Okay. So that's a new function called Lagrangian. Okay. So if you look at this new function here, essentially it's the original function you are trying to minimize and maximize it here, and plus the Lagrange multiplier, and then the constraint g of xy minus c here. Okay? Yeah. So let's take a look at what's this Lagrangian here to use here. So now, if for now temporarily, if you forget about everything that we just said here, let's just start from scratch. Let's say I'm asking you here, I'll give you a function L, right? I'll give you a function L, and I want you to find the critical point for the L. What do? Yeah, you take derivative, or you calculate what? The gradient, right? And you set the gradient to be 0. Okay, so let's say we set this guy to be 0. So if we set equal to 0, which means on calculating partial L over partial x equal to 0, partial L over partial y to be 0, and partial L to partial lambda to be 0, right? Yeah. So let's take a look at the partial derivative for each one of the term in here. So here's your L on the right side, and if I take partial L over partial x, so the first term has x, so that's good. You get partial f over partial x, right? And then second term, you got lambda here. When you take a partial derivative with respect to x, and you treat the lambda as constant, then lambda times partial g over partial x, right? And c is a constant with respect to x, so that's a 0. So you get the first term, which is this, right? Yeah. And then you take the second one, partial L over partial y, you'll get this equation right here. And the last one, when you take a partial L over partial lambda, guess what do we have? We got this term, right? Got this one here. So that's the result for taking the gradient and let it equal to 0. And if you take a look at the results at here, and that's essentially the three equations I have just wrote it down, right? It's just essentially the same equation as wrote down here. Okay? Yeah. So basically, the idea is the newly introduced Lagrangian function, which is basically becoming an unconstrained problem, right? And the results is the same as this constraint problem here. That make sense?
With an extra variable.
With an extra variable, exactly. Right? Yeah. So that's the basis that's actually for our quadratic, linear quadratic control in the next. Okay? Yeah. And just for the next step, it'll look different, but I'll guarantee, in the formality-wise, it'll be the same as the writing over here. Okay? Yeah. So I'll skip an examples. You can literally find any simple examples like the examples for this one here, right? For the examples of this, okay? And you can try to find basically the solution, right? Given these simple examples. Okay. So let me extend this just slightly at here, right? So over here, I only have one constraint, right? Over here, there's only one constraint at here. So let's say we extend it a little bit at here. Okay, let's extend it a little bit. Suppose that we have a multiple constraints. Okay, let's see, we have a multiple constraints at here. So if I have a multiple constraints, okay, so I'll write it down the situation in here. Okay. We want to maximize or minimize. Let's see, I'm still going to use this function at here. Okay. Yeah. And subject to the first constraint, the second constraint, okay. And you can literally add as many as possible. Okay. Because this is only function two variable, kind of hard to imagine, but literally, you can add any constraints, but sometimes it's not feasible, right? Sometimes it's not feasible anymore. Okay. So if I have multiple constraints at here, okay, then how do I formulate this one into the equation that I want then, right? So you can actually formulate like this. So you can introduce a Lagrangian L, and L will be x, y, and then lambda 1, lambda 2, up to lambda n. So n number of Lagrange multiplier. Okay, and this one equal to f of xy, okay, and plus, okay, lambda 1 g1 xy minus c1 plus lambda 2 g2 xy minus c2 and plus until lambda n gn xy minus cn. Right, so that's the idea, right? You have a n number of constraints that are here, and we just have to introduce n number of Lagrange multipliers at here. Okay. That's an easy extension, right? But of course, it's much more computational, right? Simple type of question. So we can write this one into a vector format, okay? A vector format here. Okay? So if you write it in a vector format at here, so that could be just basically fxy plus, okay? I introduce a lambda vector, okay? Introduce a lambda, maybe I'll write down a lambda vector first, just sorry. Yeah. Introduce a lambda vector here, which is lambda 1 to lambda n. And also introduce a vector for the constraint at here. Okay. Introduce a vector for the constraint. So g1 up to, this is minus c1 up to gn minus cn. Okay, so you can introduce two vectors here. Then that Lagrangian equation can be written in a much simpler format. So it will become lambda transpose times this g x y at here. Okay.
Do we know what those lambdas are at this point?
We don't know. That's actually the solution that we're trying to find, right? Yeah. Does that make sense? Right? So it looks much more complicated now, right? But it's in the same, exactly the same format as the simple problems, okay? Yeah. So then, if back to this question here, if you're being asked is, can you find the critical point for the function L, right? So what do? Basically, we let this gradient del L to be 0, okay? And then you're trying to find what's this one, and what is this one, right? So here you have a you have a lambda. Instead of using just lambda 1 to lambda n, you can use the symbol as partial L over partial lambda vector at here. Okay, partial L over partial lambda. Now, unfortunately, over here, right, when you see this is something actually new for our curriculum. So when you have a partial derivative over a partial vector, okay, and sometimes this is not necessarily a vector. This could be a matrix at here. Okay, so there is another branch of mathematics called the matrix calculus. It's not a very big branch, but it involves basically calculus with respect to the matrix. Okay, yeah. So I'll show you a couple of examples. This is actually what we're gonna use very shortly right here. Okay. So for example, given, let's say, given a quadratic expression, q of x equal to x transpose times a and x, and x, let's say is an n by 1 vector, and a is a n by n matrix. Okay, n by n matrix. So if you are required to calculate what is the partial derivative of q with respect to the vector x. Okay, let's say if you're required to calculate. So you can think first. Let's think about the simple case. If this is all scalar, right? If the n is equal to 1, right? If n equal to 1, this is basically x times a times x, right? Which is what? A times x squared, right? A times x squared. Okay, it's quadratic. Okay. Now, if this is not a scalar, if this is a vector here, and then you require to calculate partial q over partial x, and this one turned out to be basically a transpose x plus ax, okay, plus ax. Good? Yeah. And in our particular case, there's a very special case. If A is symmetric, okay, if A is a symmetric matrix, symmetric matrix means the transpose on the matrix is the same as itself, right? The same as itself. So basically means A transpose equal to A. Then for this particular partial derivative, you get what? 2A times x. Okay, 2A times x. Is that good?
Exactly what we get.
Yeah, exactly, right? Yeah. So matrix calculus basically is a more generous calculus, right? You know, now you have a single variable calculus or multivariable calculus. Okay? Yeah. So that is basically the quick review at here in terms of constrained and unconstrained problem at here. Okay. So now let's go into our particular question at here. Okay. Yeah. And for particular, what we're going to look at is discrete linear quadratic optimal control problem. Okay, optimal control. Okay, so I'm going to write down first of all, I'm going to write down our system that we've been always working with. Here's our system, right? Here's the system here. Is that good? Yeah. And now the question here is, you will have to consider this system now as the constraint. Okay, this is the constraint here. As a matter of fact, it's not just one constraint. You can see you have, if you expand this vector here, you have a multiple constraints here, right? You know, x1 of k plus 1 equal to gx1 of k plus u of k, right? Yeah. So this is the system here is going to be our constraint. Okay, so this system equation, the system is, it actually makes sense because your state vector, right, are not any arbitrary values. They're constrained to this particular system, okay, because you're using it to describe this system here. Now what we want to do is we wanted to, in our particular case, we want to minimize, okay, a particular function. I'm going to call it the j. Okay, so j equal to 1/2 x transpose n and s x transpose n and here plus 1/2 n minus 1 from starting from k equal to 0 x transpose k q transpose k plus u transpose times r and u of k. Okay, so this is looks different now, right? Looks different, but I'll guarantee this is actually the same thing. Okay, yeah, same type of problem here. Okay, so here is our original system at here. Okay, here's our original system, and here is a so-called function that we're going to try to minimize it here. So we do have a name for this. Okay, we do have a name. So for this name here, the different name we can call it J, can be called the performance index, or the cost function. Okay, a cost function at here, or yeah, let's keep it that way. Yeah. So let's consider this statement at here. Okay, let's look at the statement. So the statement basically is, can you find the minimum value? Right, find the minimum value for the j, and the j is a function what? Of all the state vectors and plus the control input, right? The control input. So j is a function of all the state vectors and the control input. And this function, the x at here, is subject to what? Subject to the original system state equation at here. Okay? Yeah. So if you can map to the simple question, you have a function f of x, y, right? Simple one. I'm trying to minimize it, or trying to find a minimum location, subject to a simple constraint, but now essentially here we have a little bit relative more complicated constraint in here, right? Okay. But it's still the same statement, isn't it, right? Okay. Now, second of all, let's take a look at this function j at here. Okay, so why we're trying to minimize this we're trying to minimize this cost function. And this cost function is written in a so-called quadratic form. See, right? This is basically if this is scalar format, this is essentially 1/2 s times x squared, right? Or this is 1/2 q times x squared. This is 1/2 r times u squared. Right? So it's a quadratic format. Okay? Yeah. So the whole format here. So j is a quadratic format. Okay. Yeah. And we also have a few matrix, a constant here, S, Q, and R at here inside this performance index J. So there are some specific requirements on the selection of Q, R, and S at here. Okay. So Q, R, S, okay, they are called the weighting. First of all, they are called the weighting matrices. Okay, weighting matrices. And in particular, you will pick the Q, R, and S, okay, as positive definite matrices. Okay, so you're going to pick them as a positive definite matrices. And also you will pick these three matrices as a real symmetric matrices. Okay. So here are some constraints, okay, in terms of selection of the matrices Q, R, and S. So every time you can think back in terms of scalar, right? Positive definite, basically you pick them as positive numbers, right? And simple, like, but it's not that accurate. And real symmetric, right? That's what it means basically. Okay, yeah. So now, if you come back to, based on this selection, come back to this Q, which is a quadratic format, right? Quadratic format. And guess what? What does that mean to the J here? And actually, I mentioned the one property previously. So if Q, R, S, let's even just look at one term here. If Q is a positive definite matrix, then this term must be what? Positive. Then every term will be positive, right? Every term will be positive. And this whole J term, right? This whole J term. Let's say if I give you a function J equal to 1/2 mv squared. That's quadratic, and this is positive. That's basically the whole thing is positive, right? And if you plot this J, I mean this J here, you plot it, basically, what do you see? You see a curve, and that curve is always, as V is changing, right? As V is changing, and that curve is always what? It's always pointing up, right? Like this. That make sense? If I have a multiple, maybe V1 and V2 here, okay? So then you get a surface, and that surface will always be what? Pointing up, right? It's like a bow, also pointing up here. And because they're all positive here, so I can't draw this more than function 2 variables. So you can imagine the J will be like a bow, is always pointing upwards, right? Pointing upwards. And what does that actually implicate? If you have a surface always pointing upwards, and if they have a constraint, you're moving along the constraint, there will be curve traced out along this surface. So you are guaranteed to have what? A minimum, basically, right? And this is actually a branch of in mathematics. This is called essentially called convex optimization. Right? Yeah. So for the convex, you're essentially trying to find is the minimum, because it's always pointing upwards there. Okay? Yeah. So that's why for this particular J, I didn't write the maximum. I just write down the minimum, right? Try to minimize this J at here. Is that okay? Right. So that's first thing, got to be clear. And second of all, okay, let's take a look at the formatting of the J here. Everything, the writing of the J is in the format of quadratic mv squared. Here is like a u square, right? Here is like x square. Okay? Yeah. And what is our u here? U is the control input, right? And x, if you one of the x position of velocity, this is like a v square, isn't it, right? And 1/2 mv squared we have learned representing the kinetic energy, right? Kinetic energy. So whenever you have a term like something v square, x square, or u square, so it has something to do with what? Energy. Okay, you got something to do with energy, right? Yeah. And u is your control input. So u square, that represents basically your control effort, right, into this system right here. And x square representing the state vectors square. Okay? It's not energy input, but this represents the state vectors. You know, some of the state vectors will be the outputs, basically, right? Yeah. So if you're minimizing the J, basically means what are we minimizing? We're going to try to minimize the control input to the system. At the same time, we're also trying to minimize what? The x at here, right? Trying to minimize x. See the x, u. If you want the J to be small, then you have to have a small x and a small u, right? That's the point. Okay, and that's exactly what you're trying to do. If you want to do control, you want to have a less control input, you know, basically save energy. At the same time, you want to what? Minimize the x value at here. Ultimately, if it's a regulation problem, you want everything go back to 0, right? Yeah. So that's exactly the idea what we want to achieve at here. Okay? Yeah. So and the other thing is, think about without even any calculation in here, right? Let's see if I pick a Q, okay, is 1000 here. If I pick another Q, let's say here is 10. Okay, so that's two choices of Q matrices. Okay, that's two choices of Q matrices here. And both choices I made at here are the so-called positive definite matrix, right? Yeah. And they are also both symmetric matrix. Okay. Yeah. What is the difference between these two choices, Q1 and Q2 then, right? what's the difference between this Q1 and the Q2? If you first you try Q1 as the 1000, the second you try the Q2 as a 10. What does that mean? What's the implication on the minimization of the J at here?
Larger values for Q, low tolerance, smaller values for X.
Exactly, right? Excellent. If your Q is large and you still want to minimize the J, then you don't have any other choice except what? Smaller X at here. Does that make sense, right? So this is actually give you a sense in the future when you do simulation or control, how do you pick a Q or R? If you want to have a very small errors for the X, or basically wanted to bring it back to 0 as close as possible, then you need a larger Q value basically. That make sense? Yeah. So how about the R? The R matrix. If you pick, I don't know, let's say 1, 0, 0, 1, and the other R, let's say 0.1, 0, 0, 0.1, and here. You can use the same analogy, right? If you have a smaller R matrix, that means you can have a little bit of luxury in terms of bigger what? Control input. Okay? And that actually sometimes it's very important because you want to control the system a little bit faster, right? Then you need a little bit smaller R at here. Because if your R is too big, then that naturally will suppress this U value at here, right? Yeah. And the smaller U, you put a very small control input to the system, then you don't have much of a response as fast as possible, right? Yeah. So that essentially is very simple, right? You can literally see how would you pick your Q and R, right, in terms of simulation. So now finally, what's my objective now, right? The objective here is to find the minimum value for J, okay, with respect to state vector X, control input to U, okay. So basically that's what we're trying to find the G at here, and the solution, right? The solution for U. So, because your input, you look at this one here. Your only input is a U at here. So you're trying to input certain U into the system, and the input of the U will affect the X. Together, U and X will affect the value of the J, right? So if you can find a solution, then the solution for the U, right, is basically this so-called optimal solution. Okay, and we use a U star here, okay, to represent this solution, right? So ultimately, we want to find an optimal control input U, such that the J value is minimized. Okay, yeah. And the U, okay, is if this U, as we learn in pole placement, this is our negative feedback, right? So negative K times your state vector here. If you find a U hat, which is solution here, basically you need to find this K here needs to be optimal. So that's ultimately finding an optimal solution. U leads to finding an optimal solution for the feedback gain matrix K. It just boils down to how we can find this K matrix and plug it over here, then you get an optimal control basically, right? Yeah. So from outside, it won't have any difference at all from the pole placement. You still have a feedback gain K, right? And for the pole placement, the K is obtained based on desired pole, and now your K will be obtained based on this optimal solution. Okay, yeah. So let's basically get into the details of how to derive an expression for the optimal solution K now, and this is where you can actually take a nap. I remember there's a lot of writing in here. Okay, you not all the expressions will be straightforward as is. Okay, so I'm going to use that Lagrange multiplier to introduce this Lagrangian here. Okay. So back off a little bit here. We have our constraint. We have our function that we're trying to minimize. So I'm going to use the Lagrange multiplier to introduce this Lagrangian function, right? So Lagrangian function basically means instead of using the L here, I'll use another symbol called JA. So the first part is the function that we're trying to minimize. Okay, this is the first part, right? This is the first part. That it's like that. What is it? It's like that f of x, y, right? Okay, that's the function you're trying to minimize. And then the second part is to introduce a Lagrange multiplier. Because we have a multiple constraint, so we have a vector lambda here, and also because we have multiple steps k, right? So we have a lambda of k plus 1, and here is this Lagrange multiplier. And the inside is our constraint, the bracket. Okay. So if you look at this expression, that's basically the same as our expression like the like that format, right? Same format. Right? But it's except everything is in the vector, right? Because it's not just a scalar. Good? Okay?
That's because our system is the constraint.
Yeah, the system is our constraint here. Yeah. Because your x and u cannot go anywhere but inside the system. Yeah. Okay, so now the rest of the work basically is the original optimization problem becomes the constraint problem now. Becomes what? Becomes unconstrained now, right? So all we need to do is we need to calculate the del GA equal to 0. So, and we let the gradient of this one equal to 0, and then try to solve for a solution in here. That make sense? Yeah. And because the GA here is a convex function, then the solution guaranteed will be a minimum basically location, right? It's a minimization problem. Okay. So first equation is partial JA, okay, over the partial UK. Okay, so you have a one variable here. Technically, there are more than one. There's a lot. It depends on how many inputs to the system. Right. So this is the first. You set it let equal to 0. The first partial derivative. Okay. So partial this over partial UK equal to 0. Okay. And what does that leave us? See, this is basically the only place that has a u, and then also this location has a u at here, right? There's two variables u at here, and the matrix calculus I think I showed you at here. So when you have a quadratic form like this, and you take a partial derivative, if a is symmetric, you get 2a times x at here, right? Yeah. So in here you have a r at here, so the partial derivative for this term here, you basically end up with r times uk, right? R times uk for this term. Partial derivative of this term with respect to the uk, and the partial derivative of this times this and this with respect to the uk, that gives you h transpose lambda k plus 1. Here there's another basically matrix calculus here. So if you have a partial, for example, lambda transpose f, okay, and then x at here divided by partial x, and it gives you the f transpose lambda. Okay, so you see lambda transpose h times u, it's the same format as this. When you take a partial derivative with respect to u, you get f transpose lambda, which become h transpose and lambda at here. Okay. Yeah. So this is the first equation, let equal to 0. Right. So that this derivative at here, okay, give us the first equation. Okay, let me dial a second another equation here, and then we can. Let's take a look at the partial derivative, okay, with respect to the lambda of the k plus k. Okay, our partial derivative lambda of k plus k. Now for this term in here, basically, this is the constant. This is the any other terms other than the lambda will be considered as a constant. Then, for this derivative equal to 0, you get back whatever inside the bracket equal to 0. Okay, and this is our constraint basically, right? This is our constraint in here. Is that good? Yeah. Okay. So, and third is to take a partial derivative with respect to the x. Okay. Right. You have essentially bigger variables x, u, and lambda. So last one, take a partial derivative with respect to x right here. Now this one is a little bit. I'll go in a little bit detail in the next lecture. But the results of this partial derivative give us q xk minus lambda xk plus g transpose lambda k plus 1 equal to 0. So the third partial derivative will give me this expression right here. I'll explain this third one a little bit detail in the next lecture here. But basically, you look at the terms anywhere that has x of k. Here has xk, here has xk, and we'll expand it a little bit actually to get. So now the three equations, right? So let me run. The first one is called control equation. The second one is called state equation. And the last one is called a joint equation. Okay, technically. Okay, yeah. The three equations, we try to manipulate them and to get a solution for our k at here, basically. Okay, yeah. So let's look at this in the next lecture. Okay. Yeah.